So let's investigate if this matrix is diagonalizable or not. So to start, the first step we know that is the calculation of the characteristic equation, the characteristic polynomial, a minus lambda I. So this determinant in this case is equal to 3 minus lambda. We're going to subtract lambda everywhere here. 1, 0, 0, 3 minus lambda, 0, 0, 0, 2 minus lambda. We calculate this determinant. In this case, we observe that this matrix is triangular, so the determinant in this case is just 3 minus lambda, 3 minus lambda, 2 minus lambda. And so in this case, to put these equations equals to 0 gives us solutions lambda equal 3 and lambda equal 2. So let's call lambda 1 equal 3, lambda 2 equal 2. Okay, so we highlight the first step, that is the list of all the eigenvalues of this matrix. Calculating the eigenspaces. We need the basis of the eigenspaces, right? So the first eigenvalue is lambda 1 equal 3. So to calculate the eigenspace, I'm going to write down in the matrix that we have here, instead of lambda, we are going to put now 3. So then this is going to be 3 minus 3, which is 0, 1, 0. And so 0, 3 minus 3, which is 0, 0. And then 0, 0. And 2 minus 3, which is minus 1. So this is the matrix that we have to put multiplied by the vector equal to 0. So we do the Gauss-Jordan elimination. In this case, we can see right away that this is a reduced matrix. Let's just multiply to get the equations that the vectors have to satisfy to be in this eigenspace. So from the first one, we will set that y is equal to 0. From the second one, we obtain nothing. And from the third one, we obtain minus z equals to 0. So from these two things, then we get that y and z is 0 and x is anything, right? So let's put the parameter x equal t, y equals 0, z equals 0. These are going to be the components of our vector. So our vector is t, 0, 0. So let's take the t as a common factor and we extract the base this way, and this is the base of this eigenspace. So we get that the vector 1, 0, 0 is the basis for the first eigenspace. So we got that the basis for the curve of a minus 3 of the identity is given by the vector 1, 0, 0. Okay, so we finish then the study of the problem for the first eigenspace. So we do the same now for the second one. So for the eigenspace lambda equal 2, we again construct the matrix here. So we go back to our matrix here. So we have to put lambda equal 2 now in this matrix. So that will be 3 minus 2, which is 1, and then 1, 0, 0, 3 minus 2, which is 1 again, 0, and then 0, 0, and 2 minus 2, which is 0. And so they again multiply by x, y, 0, x, y, z have to be 0. And so the reduced matrix, we have it already, and so we can say that from here, from the first equation, we get that x plus y is equal 0, and for the second one we get that y is equal 0, and for the third one we get nothing. So y equals 0, we substitute here, we get that x is equal 0. So we get that in this case x is 0 and y is 0. And z can be anything, right? So then we have that our vector is going to be x equals 0, y equals 0, and z equal parameter t. And so our vector is going to be 0, 0, t. Let's take a t as a common factor, and 0, 0, 0, 1 is going to be then the basis of this eigenspace. So we got then that the basis for the kerr of A minus 2 identity is given by the set of only one vector, which is 0, 0, 1. Okay, so we finish then the part of the calculation of the bases of the eigenspaces. So we have this base and we have this base here. So now what we need to do is to count them. Clearly are 2, right? So 1, 2 vectors. So remember that our matrix was a matrix that was 3 by 3, right? So we are in R cube, right? So we are in R3. And we got that our basis has only 2 vectors. And we got that putting together the bases of the eigenspaces, so this was the base of one eigenspace, and this was the base of the other eigenspace. So these are all the basic vectors that we have, so they are only 2. They are not enough for being a basis of R3. So that means that for this matrix, we were not able to find a basis form of eigenvectors. So because of that, this matrix is not diagonalizable. So let's check now if this matrix is diagonalizable or not. So first step, as always, we need to find the eigenvalues. So we are going to calculate the determinant of A minus lambda identity. So this is the determinant of, and we subtract lambda in the diagonal. That's all what we do. 4 minus lambda, minus 3, 0, 2, minus 1 minus lambda, 0, and then 1 minus 1 and 1 minus lambda. So this is the determinant we need to calculate. It may be useful to develop by this, to expand by this column, since we have 2 zeros in that column. So we are going to develop that way, and this is going to be equal to 1 minus lambda, which is positive, right? Plus, minus, plus, minus, plus. So then it's going to be 1 minus lambda times this determinant that is here. That will be just this minus this. So in this case will be 4 minus lambda times minus 1 minus lambda and minus 3 times minus 2, which is 6. Okay, so we do these multiplications, and this determinant is 1 minus lambda. We do distribute it here, combine like terms, and we obtain lambda squared minus 3 lambda plus 2. That we can't actually factor this one further, and this is lambda minus 1, lambda minus 2. So we put this equal to 0, and we obtain that the roots are lambda 1 equals 1, lambda equals 1, and lambda equals 2. So the two roots are going to be 1, and the second one 2. So this is then the list of eigenvalues for our matrix. Okay, so the next step is for each of the eigenvalues, we have to find the basis for the eigenspace. So now with each of the eigenvalues, we are going to calculate the eigenspace. So for instance, for lambda 1 equals 1, we are going to calculate the kerr of A minus 1 by the identity. So this eigenspace is the one that we are interested in the base. So in order to do that, we are going to write the matrix, but now we are going to subtract in the diagonal just 1, that is the value of lambda. So that will be 4 minus 1 is 3, minus 3, 0, 2 minus 1 is minus 2, 0, and then 1 minus 1 and 1 minus 1 is 0. So this is the matrix that multiplied by the vector should be equals to 0. So we do here the Gauss-Jordan reduction, and we will get that the first row is 1 minus 1, 0, and the other ones actually we can see that all cancel, right? So it's all 0, 0. So this multiplied by x, y, z equal to 0, 0, 0. That give us that this multiplied by this is x minus y equals 0, and so x equals y. So we can say that y parameter t, so we can write y equal t, so x is equal y, so x is going to be equal t, and z is going to be any other parameter, so let's say z equal r. And so we have that our general vector here is t, t, r. And so we take a t as a common factor, and we get here 1, 1, 0, plus r as a common factor, 0, 0, 1. Observe that when we actually multiply this and add, we obtain exactly this one here. Okay, so in that way, we calculate the basis of this eigenspace. So the basis here then is going to be given by these two vectors, the vector 1, 1, 0, and the vector 0, 0, 1. And then for the other eigenvalue that we have here, we'll do the same. So for lambda 2 equal 2, we are going to calculate a base of A minus 2 identity. And in order to do that, we will construct the matrix. So the matrix in this case will be to subtract here in the diagonal 2. So let's do that. Let's subtract 2 in the diagonal. And then minus 3, 0. And then 2 minus 3, 0. And then 1 minus 1. And 1 minus 2 minus 1. Okay, so this is the matrix that multiplied by the vector should be equal to 0. Applying then the reduction here, we get that this matrix reduces to the first row 1, 0, minus 3, the second one 0, 1, minus 2, and the third one gets all zeros. And so after we have the reduced matrix equals to this, we have that from the first equation here, we get that x minus 3z equals 0. From the second one, we get that y minus 2z equals 0. And for the third one, we get nothing. And so from here, we get that x is actually equals 3z, and from here, y is equal to z. And so if we call it z equal t, so then we have that x is 3t and y is 2t. And so our vector is going to be the vector 3t, 2t, t, that taken t as a common factor will be 3, 2, 1. And so we got that the vector 3, 2, 1 is the basis for this eigenspace. So the basis will be just given by this vector, the vector 3, 2, 1. Okay, so we finished then. We have all the first steps, right? We calculated the eigenvalues and we calculated the basis for each eigenspace. So now what remains is to count the vectors that we got here. 1, 2, 3, and we are in R3, so we have exactly a basis of eigenvectors. So because of that, this matrix is going to be diagonalizable. And moreover, we can say what is the diagonalization. We can say that the matrix P is going to be given by these vectors written as columns. So I write the first one as a column, 1, 1, 0, the second one as a column, 0, 0, 1, and the third one as a column, 3, 2, 1. That's the matrix P. Then you will calculate by any of the methods that you know of calculating inverse matrices. you will calculate the inverse of this matrix. So we will get that the inverse matrix of this by any of the methods, you will get this matrix here. Can be calculated then by Gauss-Jordan elimination, or you can calculate it also by cofactors. So in any case, given the matrix P that is formed with the eigenvectors as columns, we can calculate the matrix P, and then we calculate the P inverse by any of methods of calculating inverse matrices. And then the diagonal matrix is just the matrix that has the eigenvalues in the diagonal. Remember that this eigenvalue, the 1, 1, appear twice, right? So it would be 1, 1, 2. These are the eigenvalues in the same order that the bases here, and zeros everywhere else. So in this way, we have here all the matrices involved in the diagonalization of A. And with these matrices, we can say that if we do the multiplications of A, P, and the result we multiply by P minus 1, I mean these matrices that we have given here, the result should be the matrix D. So you should do this multiplication and check that the result that you get is exactly the diagonal matrix D.